What if the first stars in the universe just showed up in our data and we're only now realizing what we're looking at? Not theory, not a simulation, actual light from actual objects that may be the first generation of stars that ever existed. We may have just seen the first stars, ever. 13 billion light-years away, in a galaxy tagged with the very boring name LAP-1b, James Webb picked up a signal that is anything but boring. This little galaxy is blasting out radiation that normal stars should not be able to produce in that kind of environment. On paper, it looks wrong. In reality, that wrongness is exactly what you'd expect if you were finally staring straight at population 3 stars, the first stars in the universe. Let's lock down what that distance actually means, because 13 billion light-years is easy to say and hard to feel. A light-year is how far light travels in 1 year. Light is the fastest thing in the universe. Nothing outruns it. The photons from LAP-1b have been moving through space for around 13 billion years without stopping. No resets, no breaks. So when those photons hit JWST's mirror, you are not seeing a LAP-1b today. You're seeing it as it was when the universe itself was only about 800 million years old. That's insanely early. The universe is about 13.8 billion years old now. So LAP-1b is showing you a frame from the very start of the movie, long before galaxies like the Milky Way have taken shape, long before planets, long before anything that looks remotely familiar. Space is still mostly dark, mostly empty, mostly hydrogen and helium gas slowly falling into invisible dark matter structures. And in that bleak setup, somehow, this tiny galaxy is already screaming in ultraviolet. Here's the big claim. LAP-1b doesn't just look like any random early galaxy. It lines up with 3 very specific predictions for population 3 star systems. Predictions people have been arguing about for decades. First, it has an insane ultraviolet output. The amount of high-energy ionizing radiation it seems to pump out is more in line with very massive, very hot, metal-free stars than with ordinary stellar populations. Second, the gas around it appears to have almost no metals. Third, the whole system looks young, compact, and primitive. Exactly the kind of place where first-generation stars are supposed to live. That metal word sounds small, but this is the key. In astronomy, metals is a catch-all term for any element heavier than helium. Carbon, oxygen, nitrogen, silicon, iron, everything that makes rocks, water, and life possible counts as metals. Normal stars, even early ones, usually form in gas that already has some metals mixed in, because previous stars have lived and exploded and polluted their neighborhoods. Population 3 stars are different. They are supposed to form from untouched Big Bang gas, almost pure hydrogen and helium with tiny traces of lithium. No carbon, no oxygen, no iron. Clean, primitive fuel. So when you see a system like LAP-1-b that is blasting out extreme ultraviolet and yet shows almost no metal emission lines in its spectrum, that's not just interesting. That's a huge red flag that says this gas hasn't been through many, or maybe any previous rounds of star formation. This is the kind of environment where first-generation stars can still exist, even hundreds of millions of years after the Big Bang. Now, add the second piece: power. The radiation coming out of LAP-1b is not gentle. The ultraviolet output looks more like a cluster of monsters, stars tens to hundreds of times the mass of the Sun, than like a calm, steady population of smaller, metal-rich stars. Big, hot stars emit brutal amounts of high-energy light. That light slams into the gas around them, strips electrons off atoms, and makes the gas glow in specific lines we can see. LAP1b's spectrum screams overpowered in exactly the way you'd expect from a population dominated by very massive, very primitive stars. This is not subtle. If the interpretation is right, you are watching the universe as it turns on some of its first real light sources. That's the level of stakes we're talking about. Before these stars, the universe is mostly dark. After these stars, the universe starts to change fast. Hydrogen between galaxies gets reionized. Heavy elements get forged. The raw materials for planets, chemistry, and biology start to exist. LAP1b isn't just another dot in a catalogue. It's a snapshot of the moment the universe starts to build everything else. But there's a brutal truth here. Objects like LAP1b should be almost impossible to see. It's too far, too faint, too small. Even for a monster space telescope, this should be out of reach. So how are we doing this? How are we pulling light from the edge of cosmic history and turning it into a spectrum on a graph? 2 words: unfair advantage. First advantage, JWST. That 6.5-meter mirror is a light bucket on steroids. It collects about 6 times as much light as Hubble's mirror. It's optimized for infrared wavelengths, which is exactly where the stretched, redshifted light from these early galaxies ends up. Webb is a machine built for this job. It doesn't just see far, it sees early. Second advantage, gravity itself. LAP1b is not sitting alone on the sky. It just happens to lie behind a massive foreground cluster of galaxies. That cluster's gravity warps space-time. Light from LAP1b passes through this warped region and gets bent and amplified toward us. This is gravitational lensing. The cluster becomes a natural telescope. It magnifies LAP1b by something like a factor of 100. Without that boost, LAP1b would be invisible. Not hard to see, just gone. So stack the factors. You have a universe that leaves behind patches of nearly pristine gas. Gravity collapses those patches into brutal, short-lived, metal-free stars. Those stars cluster into a tiny, hyperactive galaxy. That galaxy sits in exactly the right line of sight behind a huge cluster. The cluster's gravity magnifies it by about 100 times. A $10 billion infrared space telescope with a huge mirror parked 1 million miles from Earth stares at that region long enough to collect its photons. And then, finally, human eyes and human code decode those photons into a spectrum that says extreme UV, almost no metals, primitive environment. That's not an everyday detection. That's a cosmic setup that has been running for billions of years, waiting for one species with telescopes and computers to finally notice it. So here's the blunt version. If LAP and MAP1-b really is what it looks like, then we are no longer just talking about population 3 stars as theoretical. We are watching their possible light in real data. You are alive at the moment when the universe starts giving up the details of how it lit itself up for the first time. That's not a small update that rewrites how we anchor the entire story of structure forming in the early universe. But there's a deeper question hanging over all of this, before LAP1b, before any galaxy, before any star. How did the universe set the stage? How did we go from a hot, dense fireball to a cold, dark, almost featureless cosmos where these first stars could form at all? To understand why LAP1b is such a big deal, we have to drag the clock all the way back to a universe that has basically nothing going on yet. And that's where things get even more unsettling. How do you get a universe full of stars, planets, and people from a universe that basically has none of the ingredients for any of that? That's the disturbing part. At the beginning, the universe is not almost ready. It is useless. If you were dropped into that early universe, there is nothing for you. No solid matter, no atoms you're made of, just a hot, expanding mess that should not obviously lead to you sitting here watching this. Right after the Big Bang, the chemistry is brutal in its simplicity. This is the post-Big Bang chemistry phase. The entire observable universe is mostly hydrogen and helium, with a tiny sprinkle of lithium. That's it. No carbon, no oxygen, no nitrogen, no iron, no silicon. None of the stuff that makes rock, air, water, or biology. The periodic table you learned in school? Almost all of it doesn't exist yet. You've got basically 2.5 elements to play with in a volume of space that is expanding and cooling as fast as physics will allow. That's important because it means one thing. Stars, planets, and life cannot just appear. The universe has to build the heavy elements first, and it has to do that using only this pathetic starter kit. Hydrogen and helium gas, spread out and thinning, in a space that is getting bigger every second. It's like trying to build a city when all you have is air and time. So what happens when that first hot phase calms down? What does a universe with almost no structure actually look like? After about 380,000 years, something big shifts. Electrons slow down enough to stick to protons and form neutral atoms. Light that was trapped starts to travel freely. That relic glow is what we now see as the cosmic microwave background. And then, after that, the universe goes dark. This is what cosmologists call the Dark Ages. No stars, no galaxies, no glowing gas clouds, just neutral hydrogen and helium, slowly cooling, sitting in a growing cosmic web of dark matter. Think about that. Hundreds of millions of years where nothing shines. Space is not full of stars. It's full of invisible dark matter halos pulling in gas, and that gas just sitting there, cooling and clumping, but not yet crossing the line into star formation. The only light left is that fading microwave background. If you were somehow there with normal human eyes, you'd see nothing. No points of light, just black. So how long does the universe stay like that? When should stars actually start turning on? This is where precise measurements come in. Data from the Planck satellite and other observations let us reconstruct the timing. The best models say that large-scale star formation really kicks off roughly 300 million years after the Big Bang. That's incredibly early, but not instant. For 300 million years, the universe is basically just preparing. Dark matter halos grow, gas falls in, gas cools, and at some point, gravity wins and cores get dense and hot enough to ignite nuclear fusion. Cosmologists describe these early times with a number called redshift, Z-AID. The higher the redshift, the earlier in cosmic time you're looking. That first major wave of star formation sits around redshift Z, approximately 10 to 15. That's the era when you expect the first big populations of stars and tiny galaxies to really start carving into the darkness. This is the window where population 3 stars are supposed to appear. Massive, metal-free stars forming out of untouched hydrogen and helium in young halos. So what do these first stars actually do to a universe that has been dead quiet for hundreds of millions of years? They change everything. The first stars are the switch that ends the Dark Ages. When these objects turn on, they pour out high-energy photons. Those photons blast into the neutral hydrogen surrounding them, rip electrons off the atoms, and turn the gas from neutral to ionized again. This process is called reionization. It's not optional. It reshapes the universe. The fog of neutral hydrogen that was blocking light between galaxies starts to thin out. The universe becomes transparent to ultraviolet light again. You go from a dark, neutral, boring cosmos to a hot, carved-up, glowing one. At the same time, inside those first stars, nuclear fusion starts doing serious work. For the first time ever, heavier elements are created in large amounts. Carbon, oxygen, silicon, iron. These show up in stellar cores and get blasted into space by supernova explosions. That's the start of heavy element production. This is where the raw materials for planets, chemistry, and life start to exist. Without that first generation of stars, the universe stays stuck with hydrogen and helium forever. No rocky planets, no oceans, no you. So when we talk about why first stars matter, this is not an academic detail. This is the line between a universe that can't make complex structures and a universe that absolutely can. If we don't understand when and where these first stars formed, we don't understand how any later galaxy, including the Milky Way, ended up with the metals, the gas physics, and the structure we see today. If we get the timing wrong, our story of cosmic history is broken. Now bring LAP 1b back into this. You're not looking at it 300 million years after the Big Bang. You're seeing it at around 800 million years after the Big Bang. At redshift about 6.6. That's later than the very first star formation wave, but still extremely early. By that time, in many regions of the universe, several generations of stars should already have formed and exploded. Metals should be mixing into the gas. Things should be dirty. The Dark Ages should be over. Reionization should be well underway, or nearly finished. So here is the sharp, dangerous question LAP 1b is forcing. When you look at that galaxy 800 million years after the Big Bang, are you seeing a region that has already been enriched by earlier generations of stars? Or are you seeing a pocket of space that somehow stayed almost untouched, so clean that population 3 stars can still form there? If LAP 1b is heavily enriched, full of metals, then it's just another early galaxy. Useful, interesting, but not revolutionary. It fits the idea that the universe rapidly polluted itself with heavy elements and moved on. But that's not what the spectra suggest. What you see looks almost pristine. Intense ultraviolet power with almost no metal lines. That points to gas that has barely been processed, even after hundreds of millions of years. That should not be easy. By this time, supernova explosions from earlier stars should have sprayed metals all over the place. Finding a region this clean, this late, means the universe didn't just flip a switch and instantly fill itself with heavy elements. It kept little isolated pockets of near pristine gas alive, protected, and ready to make fresh population 3 stars much later than the first wave. If that's true, then LAP 1-b is not just a random galaxy in the early universe. It's a test. Did this part of space already go through multiple generations of star formation, or is it still so primitive that we are watching the first wave hit it in real time? That's the stakes. We're not just asking, are there population 3 stars? We're asking, how long did the universe keep these first generation conditions alive, and how many times did it run this first stars experiment? And that leads to the next brutal step. If these stars are really that primitive, that massive, and that short-lived. What exactly are they like? Because they are not just older versions of the stars you know. They're something much more extreme. What kind of star is so extreme that the universe basically had to get rid of all of them before you ever showed up? That's what population 3 stars are. They're not just old stars. They are a separate category of object, born in conditions that will never exist again. If normal stars are the everyday background, population 3 stars are the one-time cosmic event that rewired everything and then vanished. Let's start with the basic definition, because the language here is sneaky. In astronomy, metals do not mean coins or jewelry. Metals means any element heavier than helium. Carbon is a metal. Oxygen is a metal. Nitrogen, silicon, iron, all metals in this context. Now, look at population 3 stars. They are metal-free, or as close as nature can realistically get. They form out of gas that has only hydrogen, helium, and a tiny trace of lithium. No carbon to help gas cool. No oxygen. No iron. Just raw, Big Bang leftovers collapsing under gravity. So here's the question. If you strip away all the heavy elements that help gas fragment and cool today, what kind of stars do you get? You don't get calm, sun-like stars. When gas can't cool efficiently, it doesn't break into lots of small clumps. It collapses into fewer, much bigger ones. That immediately pushes population 3 stars into a completely different regime. Simulations are pretty ruthless about this. They suggest many population 3 stars were tens to hundreds of times the Sun's mass. Not a little bigger, orders of magnitude bigger. Some models push them up to several hundred solar masses. A star like that does not behave politely. A star with 100, 200, 300 times the mass of the Sun is a nuclear reactor running near the edge of what physics can handle. The core gets extremely hot, and the amount of ultraviolet radiation it throws out is brutal. That's the second piece. Power. Population 3 stars should blaze with extreme UV radiation. Their surfaces are much hotter than most stars you're familiar with. Hotter surface means more high-energy photons. That radiation slams into the gas around them, ionizes hydrogen and helium, and creates the kind of strong emission lines JWST is now seeing in targets like LAP-1b. These stars don't just light up their neighborhood, they attack it. So now you've got a universe with these oversized, metal-free monsters turning on in small halos. Next question. How long do they last? The answer is simple and aggressive. Basically, not long at all. A very massive star burns through its fuel fast. A 100 solar mass star is not living for billions of years. It burns out in just a few million years. Compare that to the Sun, which has a total lifetime of around 10 billion years. These things are cosmic fireworks, not candles. They ignite, they blast energy into their surroundings, and they die quickly. This is where the story gets harsh for anyone who wants to see one nearby. Because population 3 stars live fast and die young, none of them should survive to the present day. Every single population 3 star that formed in the early universe is dead now. Not most of them, all of them. By the time the Milky Way looks anything like a normal spiral galaxy, population 3 stars are gone. What's left is not the star, but its impact, the heavy elements it created and threw into space when it exploded. So why don't we find one hiding somewhere in our galaxy? Why can't we just aim a telescope nearby and say, that's one? Because that's not how the timeline works. Population 3 stars formed in the absolute earliest, most primitive gas. Their explosions polluted the surrounding material with metals. Later generations of stars formed out of that enriched gas. Those later. Stars can live much longer, including many that are still around today. But the original monsters that made the metals, those are long gone. That means we can't hunt population 3 stars directly in our own neighborhood. You're never going to walk into a lab, pull up a Hubble image of some local star, and label it confirmed population 3. The physics says they died out billions of years ago. The only thing they leave behind inside our galaxy are chemical fingerprints, weird abundance patterns in some of the oldest, most primitive Milky Way stars. Those second-generation stars carry the signature of population 3 explosions in their atmospheres, but they are not population 3 themselves. So if you can't find them nearby, where do you look? You have to go after them the hard way, in the distant universe. And in cosmology, far away literally means long ago. The farther out you look, the further back in time you are seeing. To catch population 3 stars in the act, you must look at galaxies from the first few 100 million years of cosmic history, when the universe was still young, messy, and full of places where gas was almost pristine. That's what makes targets like LAP-1b such a big deal. You're not expecting population 3 stars to be sitting in some random modern galaxy. You're expecting them in small, early systems at high redshift, where at least some gas is still barely touched by previous star formation. Those are the only places left in the universe where the conditions even come close to what population 3 stars need: zero metals, dense halos, and time to collapse. So here's the observational puzzle in one line. You will never see a clean, isolated population 3 star in the Milky Way. If you want to see them, you have to go to insane distances, insane look-back times, and you have to use the most powerful telescope humanity has ever built, plus gravitational lensing, just to get a faint, blended glimpse of their combined light. That's why the search has taken decades. Strong UV, zero metals, short lifetimes, and only existing in the earliest times. That combination makes population 3 stars almost designed to hide from you. You are chasing objects that died billions of years ago, that never existed nearby, that only formed in rare, primitive pockets, and that now can only be studied by reading subtle signatures in the spectra of tiny, distant galaxies. So, when a system like LAP-1b shows up with ridiculous ultraviolet output, almost no metal lines, and a primitive environment, it's not just interesting. It's breaking into that locked room. It's the kind of signal you expect if those zero-metal, maximum chaos stars are finally on the edge of being exposed. But there's another problem. If you can't see an individual population 3 star, and they only existed in the early universe, how do you actually prove they were there at all? What do you look for in the light to say, this is them, not something else? To answer that, you have to stop thinking in terms of pretty pictures and start thinking like a forensic scientist, reading spectra as a crime scene report from 13 billion years ago. How do you track down a star that has been dead for 13 billion years? You don't. You have no chance of seeing it directly. The star is gone, its light is over, its matter is scattered. What you can do is much colder. You read the light it forced its environment to emit, long after the star itself has disappeared. You're not seeing the criminal, you're reading the crime scene. Here's the core trick: spectral lines. Spectral lines are not optional background details. They are the entire method. Every element absorbs and emits light at very specific wavelengths. Hydrogen does it at certain exact wavelengths, helium at others, oxygen, carbon, nitrogen, iron. Each one has its own pattern. When you spread out the light from a galaxy into a spectrum, you see bright and dark lines at particular places. That pattern tells you what atoms and ions are in the gas, how hot they are, how ionized they are. Astronomers use this like a barcode. You don't just see a blob of light. You see a list of ingredients and physical conditions written into that light. So the question becomes brutal and simple. If population 3 stars existed, what should their barcode look like? First rule: no metals allowed. Population 3 stars form out of gas that has almost no elements heavier than helium. So, if they dominate a system, the light from that system should scream extreme radiation without showing the normal metal emission lines we're used to. In a regular young galaxy, you see strong lines from oxygen like O3, strong lines from carbon like C3, plus other metal lines. Those are the signatures of gas that has already been polluted by earlier generations of stars. For population 3, that should not be the case. You still want very strong ionizing radiation because these stars are massive and hot. But when you look at the spectrum, the usual oxygen and carbon lines should be extremely weak or missing. You want the violence without the metals. That combination is rare. You don't just need hot stars. You need hot stars in almost pristine gas. That's the exact configuration early universe simulations keep predicting for population 3 clusters. But high energy plus no metals is not specific enough. You could, in principle, get harsh radiation from other sources like active black holes or weird compact stellar populations. So you look for an even sharper tracer. This is where helium comes in, and it's not just any helium signal. One key line is He2 lambda 1640. That's an emission line from helium that has been doubly ionized, meaning helium atoms have lost 2 electrons, not just 1. To do that, you need extreme ultraviolet photons. Normal star-forming populations often don't produce enough of those photons to make a strong He2 1640 line. Very hot, very massive, metal-poor stars do. So when JWST takes a spectrum of a high redshift galaxy and you see a strong He2 1640 line, your alarm bells go off. It tells you, in this system, there is a source producing very high energy photons. It does not prove population 3 by itself, but it narrows the field fast. Some high redshift galaxies JWST has looked at already show this kind of He2 feature. That's why. People got excited about objects like GNZ11. They had this helium ionization signature hinting at something more extreme than normal stars. But you're not done. You still need to ask, what does the rest of the light look like? Population 3 dominated systems should not only have specific lines, they should also have unusual overall colors. In particular, they should look extremely blue in the ultraviolet. There are 2 reasons. First, the stars are very hot, so they naturally emit a lot of short wavelength, high energy light. Second, the surrounding gas and dust are not yet loaded with metals. Metals and dust tend to absorb and scatter blue and UV light and make things look redder. If metals and dust are missing, that reddening is weak. So the combination of hot stars plus clean gas gives you a very blue spectral shape in the UV. So now, put these pieces together into a hard checklist. If you're hunting for population 3 signatures, you want a system that has intense ionizing UV radiation, a strong, or at least notable, He2 1640 signal, and a disturbing lack of the usual metal emission lines. On top of that, you want its overall color in the UV to be very blue. If you get all of that at once, in a very early galaxy, you are not looking at a normal stellar population. you are staring at something that fits the predicted signature of population 3. That's exactly the goal in Lab 1b. Astronomers are not guessing. They are going down this checklist line by line. They take Webb's data, spread the galaxy's light into a spectrum, and ask, is the UV output insane? Do we see evidence of very high energy photons ionizing the gas? Do we see Hertz 1640, or at least hints of it? And at the same time, are the standard metal lines either extremely weak or totally absent, down to the sensitivity limit? The answer, so far, is dangerous. Yes, on the power. Yes, on the primitive look. Yes, on the lack of metal lines, and a strong hint toward the right kind of helium behavior and UV color. LAP1b spectrum is not just unusual. It matches the pattern people wrote down in theory papers years before JWST launched. The light we are now recording from this galaxy fits expectations for a system where population 3 stars are active or recently active. You are basically reading the light from a galaxy 13 billion light-years away and seeing the imprint of stars that are already dead, whose individual photons have long faded. What survives is the way they beat up their surroundings while they lived. That's what the spectrum is showing you, not the stars themselves, but the damage they did. And here's the catch that raises the stakes again. To even get that spectrum, you need a machine built exactly for this job, at exactly this time in history, staring exactly where it needs to stare. This kind of spectral crime scene work only exists because James Webb is out there, cold, stable, and tuned to the right wavelengths. So, the next question is obvious and heavy. What kind of telescope do you have to build to do this kind of autopsy on the first stars in the universe? And how did we end up with a $10 billion time machine aimed right at galaxies like LAP1b? What kind of machine do you build when you want to spy on the first stars in history? You don't upgrade a telescope a little bit. You build James Webb. You build a $10 billion time machine, park it 1 million miles from Earth, freeze it to near absolute zero, and point it straight at the part of the universe where reality is just starting to turn the lights on. This thing exists for one core question. What were the first stars like? Here's the first brutal fact. If you want the first stars, you have to work in the infrared. Not because it's trendy, because the universe forces you. The cosmos is expanding. That expansion stretches light as it travels. Photons that left the first stars as blistering ultraviolet get dragged to longer and longer wavelengths over billions of years. By the time they reach us, they're not in the UV anymore. They're in the infrared. If you only look in visible light, you are basically blind to that early era. So JWST is tuned like a sniper on the exact wavelength range where those ancient photons now live. Roughly 0.6 to 28 micrometers. That's the sweet zone where light from the first galaxies, the first waves of star formation, the population 3 era, shows up after all that stretching. This isn't an accident. Webb's entire design is locked around that band. Detectors, optics, cooling system, everything is built to suck in those old redshifted photons and nothing else. But tuning to the right wavelength isn't enough. These early galaxies are tiny and unbelievably faint. If you don't collect a ton of light, you see nothing. That's where the mirror size becomes non-negotiable. JWST's main mirror is 6.5 meters across. That's more than 6 times the light collecting area of Hubble. That one number is the difference between this galaxy might as well not exist and we can actually get a spectrum. Every extra photon counts. Light from LAP1b has been traveling for about 13 billion years. By the time it hits JWST, there are not many photons left per second per square meter. A small mirror would collect almost none. Webb's huge segmented mirror drags in enough to turn a meaningless trickle into usable data. That's why galaxies like LAP1b, which would be invisible noise for older telescopes, suddenly show up as real targets. Without that 6.5-meter monster, this story doesn't happen. So you've got the right wavelength range and a giant mirror. How do you actually go from "there might be something there" to "this object has the spectral fingerprints of population 3 stars"? That's where the instruments matter, and they are not generic cameras. They're precision tools aimed straight at this problem. First, NIRCam. Think of NIRCam as the deep field hunter. It takes incredibly sensitive images across multiple filters in the near-infrared. You use it to sweep the sky, to stare at one patch for a long time, and to pull out ultra-faint, high redshift objects that would vanish in shorter exposures. That's how you even find candidates like LAP-1-b in the first place. They pop up as weirdly bright in certain filters, with colors that scream very high redshift. Then, once NIRCam has done its job and flagged the suspects, you hand them over to NIRSpec. NIRSpec doesn't care about pretty pictures. It rips the light apart into spectra. That's where you go hunting for a 2-1640, for strong hydrogen lines, for the eerie absence of metal lines like O3 and C3. That combination, intense ionizing UV signature plus missing metal lines, is exactly what you need to test. Is this consistent with population 3? It's the same toolset used to dissect galaxies like GNZ11. Now, it's being turned on objects like LAP1b with the same brutally specific goal. But even with all that tech, you don't just point JWST anywhere and magically catch early galaxies. You need strategy. You need to stare at the right part of the sky for a long time, and you need to exploit every advantage the universe gives you. That's where deep fields and galaxy clusters come in. For LAP1b, JWST didn't just look at some random empty region. It stared at a massive foreground galaxy cluster called MACS J0416. Why? Because that cluster is a gravitational lens. Its mass warps space-time and magnifies background galaxies. When Webb stares at MACS J0416 long enough, it's not just observing the cluster. It's using the cluster as a natural boost, pulling up background galaxies that would otherwise be too faint to detect at all. LAP1b is one of those background systems, dragged into visibility by lensing plus long exposure time. This approach is not some side quest. From day one, JWST observing programs were designed to do exactly this. Deep fields focused on strong lensing clusters, long integrations, multi-filter imaging with NIRCam, followed by NIRSpec spectroscopy on the weirdest, most distant sources that pop out. The entire pipeline is built to find precisely the kind of extreme, primitive galaxies where population 3 signatures might show up. So here's the key point. The LAP1b dataset is not an accident. It's not a lucky fluke. It's the direct payoff of a plan that has been sitting in proposals and design documents for years. Build a huge cold infrared telescope. Give it instruments that can image faint redshifted galaxies and tear their light into detailed spectra. Point it at massive galaxy clusters to use their gravity as extra magnification. Let it stare long enough that the early universe's rarest, most primitive systems finally cross the line from invisible to measurable. And when you do that, you get what we're looking at now. A magnified high redshift galaxy whose spectrum lines up with all the theoretical predictions for a population 3 hosting system. That's not random. That's the early universe finally becoming observable at the level theorists have been demanding for decades. But even with Webb's mirror, its wavelength coverage, its instruments, and its strategy, one key ingredient is still missing from this picture. You're relying on something you didn't build, something you can't control, something that warps light on a scale no human technology can match. If JWST is the time machine, then what is the cosmic zoom lens that makes galaxies like LAP-1b even show up in the first place? And how far can we push that trick before the universe stops cooperating? What do you do when even your biggest, most expensive telescope still isn't good enough? You cheat. You use the universe itself as part of your instrument. You hijack gravity to bend light for you. To see the tiniest sparks at the edge of time, you steal gravity's optical tricks. Einstein saw this coming in the math long before anyone could actually use it. General relativity says mass doesn't just sit in space like a rock on a table. Mass warps space-time itself. Light doesn't travel in straight lines through some fixed stage. It follows the curves in space-time. Put a really massive object between you and something in the background, and the path of the background light gets bent. If the mass is big enough and the alignment is good enough, that foreground object acts like a gravitational lens. It can magnify background galaxies by factors of 10, 50, even 100 or more. Not metaphorically, literally brighter, literally bigger on the sky than they would be without the lens. Your telescope plus gravity together become a combined system you could never build in hardware alone. So, what does that look like in practice when you're chasing something like LAP-1b? You need a foreground monster. In this case, it's a galaxy cluster called MACS J0416. This cluster is enormous, hundreds of galaxies, plus a huge halo of dark matter, all locked together by gravity. The total mass is so large that it reshapes space-time around it. Background light doesn't come through in straight beams. It comes through warped, bent, and in many cases focused. For LAP-1b, MACS J0416 is doing the heavy lifting. LAP-1b is not part of that cluster. It sits billions of light years behind it, much farther away. But from our point of view, it lies behind the cluster on the same line of sight. So the light leaving LAP-1b travels across the universe, hits the warped spacetime near MAC SJ0416, and gets bent toward us. That bending is what boosts the brightness. Webb is pointed at MACS J0416, but what it actually picks up includes strongly magnified background galaxies, with LAP-1b among them. Here's the brutal number. The team estimates that LAP-1b is being magnified by roughly 2 orders of magnitude, about a 100 times boost. That isn't a small correction. Without that magnification, LAP-1b would be so faint that even JWST, with its 6.5 meter mirror, would not see it as a usable object. It would fall below the detection limits. No clean detection, no spectrum, no population 3 discussion, nothing. With MACS J0416 acting as a lens, LAP-1b is yanked across that visibility threshold and turned from undetectable into measurable. You are right at the edge of what physics and engineering together can pull off. Gravitational lensing doesn't just brighten objects, it distorts them. That's why, in deep JWST and Hubble images of lensing clusters, some background galaxies look like stretched arcs, smeared lines, or repeated clumps. You're seeing multiple light paths from the same background object arriving along different routes around the cluster. The mass distribution in this lens, the galaxies plus dark matter, sets the exact pattern. The geometry of those arcs, their positions and shapes, is not just eye candy, it's data. For L81b, those distortions are how you work backward from what Webb sees to what LAP1b is really like. The team builds a detailed model of the mass in MACS J0416, then uses that model to reconstruct how much the background light has been stretched and amplified. That lets them correct the observed brightness and size of LAP1b to get its true intrinsic properties. How luminous it really is, how massive it really is, how compact it really is. Without that modeling, you'd be fooled. You'd think you were looking at a brighter, bigger galaxy than actually exists. This is not a cosmetic step. It changes the stakes. If, after correcting for lensing, LAP1b still has insane ionizing power for its mass, still looks compact but overpowered, still sits in the regime where population 3 clusters are predicted, then you're dealing with a real physical outlier, not just a lensing trick. That's the whole point of building lens models. Strip away the distortion and see what the galaxy is really doing. Here's where the tension jumps. Lensing doesn't just help you see the galaxy, it's the only reason you can even dream about isolating the light from population 3-like stars inside it. These stars are rare. They sit in small, early systems. Their combined light is weak. JWST alone, even at full power, is not enough to pull out their spectral fingerprints in most places. You need the cluster lens to take that faint signal and drag it over the detectability line. No lens, no LAP1b spectrum. No LAP1b spectrum. No population 3 candidate. So stack the dependencies. You depend on general relativity being correct so that space-time warps and lenses work at all. You depend on a massive galaxy cluster forming in exactly the right place, at the right redshift, with the right mass distribution. You depend on a tiny background galaxy like LAP1b forming directly behind it, at a much higher redshift with nearly pristine gas and extreme stars. You depend on that alignment being tight enough to give you a roughly 100 times boost in brightness instead of just a slight stretch. And then you depend on JWST being aimed at that cluster for long enough that the background galaxies show up in deep imaging and get follow-up spectroscopy. This isn't casual. It's a chain of cosmic and human conditions that has to hold together perfectly. Break any link, no lensing cluster, no background galaxy, no alignment, no JWST, and you never hear the name LAP1b. Population 3 stars stay locked in theory, hidden behind the sensitivity limits of your instruments, forever. Gravitational lensing is the universe giving you one chance to see things you were never supposed to see. It turns the most massive structures in the cosmos into accidental telescopes aimed at the early universe. And in this case, it's not just helping you refine measurements. It's the only reason these first star candidates are on the table at all. Now that you've stolen gravity's help and squeezed every photon you can out of LAP1b, there's no excuse left. You've got the lens, you've got the telescope, you've got the spectrum. The next step is simple and brutal. Stop talking about the setup and look your target in the face. What exactly is LAP1b, this tiny, distant galaxy that refuses to behave like a normal object and looks way too clean and way too intense for its age? Why does this one tiny galaxy, out of everything JWST has seen, look like the universe forgot to age it? By the time we're seeing LAP-1b, space is already messy, heated, and enriched in most places. But this object shows up looking too clean, too hot, too intense for its time. That's why it's the main suspect. Start with the basics. Where in cosmic time is this thing, really? LAP-1b sits at a redshift of about 6.6. That number isn't decorative. Redshift Z, approximately 6.6, means the light we're seeing left the galaxy when the universe was roughly 800 million years old. Not at the very first spark of star formation, but still extremely early, right in the tail end of the reionization era, when the last pockets of neutral hydrogen are being carved apart by young galaxies and their radiation. By this point, many regions of the universe have already gone through several rounds of star formation and supernova explosions. In most places, the gas should be dirty, carrying metals from earlier generations of stars. LAP-1-b is not where you'd expect to find a near-pristine environment. Yet that's what the data keeps pointing to. Now, where is it on the sky, and how did it even show up in the first place? This galaxy was spotted behind the massive foreground cluster MACS J0416 in JWST observations. The cluster is the gravitational lens. JWST stares at MACS J0416, pulls in ridiculous amounts of data, and buried in those stretched arcs and faint clumps is LAP-1b, a heavily magnified background galaxy. It's not some random catalogue entry. It got flagged because its colours and brightness, once you account for lensing, looked wrong for a normal early universe object. That triggered deeper analysis, the kind that landed as a detailed study in Astrophysical Journal letters in late 2025, laying out the case that this is not just another young galaxy. It's something sharper and stranger. So what, exactly, is wrong with it? Start with the ultraviolet output. When you take LAP-1b's spectrum and look at the emission from ionized gas, you see very strong ionizing UV radiation. The lines that trace hydrogen recombination, the overall energy needed to light that gas up, all point to a source that's hitting the gas with more high-energy photons than you'd expect from ordinary metal-rich stars of the total mass. If you tried to fit this spectrum with a standard stellar population like we see in typical galaxies, you'd find you need stars that are hotter and more intense than usual. That's already a red flag. Now add the next piece. The metals, or rather, the lack of them. In a normal early galaxy, you see clear metal emission lines in the spectrum. Oxygen lines like O3, carbon lines like C3. These lines are how we know gas has been enriched by previous generations of stars. But in LAP-1b, those usual suspects are either extremely weak or simply not there, down to the sensitivity limits of JWST's instruments. You have strong ionizing radiation and glowing gas, but the standard metal lines are suppressed. That points to very low metallicity in the gas and in the stars driving the light. Put those two facts together and the picture gets uncomfortable. This is a galaxy that is small, at a time when the universe has already had 800 million years to form and explode stars. Yet it looks like it's running on almost untouched fuel. That's where the modelling comes in. You don't just eyeball the spectrum and shrug. You plug these observations into population synthesis models, codes that simulate what a galaxy's light should look like for different stellar populations, metallicities, ages, and star formation histories. For LAP-1b, those models point to a compact system hosting a concentrated burst of very massive stars, not a gentle, drawn-out history, a sharp, intense, recent starburst. So now you're looking at a tiny galaxy, magnified by lensing, whose true intrinsic size is small, whose mass is modest, but whose radiation field is ridiculously strong for that mass. The simplest way to fit that is a high fraction of very massive, very hot, very low metallicity stars. That is exactly the kind of environment where population 3 clusters are predicted to appear. Not in big, evolved galaxies, but in small, dense, primitive systems undergoing a short, violent burst of star formation. The word pristine starts to make sense here. Not in the sense of nothing ever happened, but in the sense of very few previous star generations have polluted this gas. At Xae approximately 6.6, that is not the default expectation. The universe is already fairly busy by then, and metals from earlier supernovae should be spreading. LAP1b looks like a pocket that stayed sheltered or inefficient at forming stars until relatively late. So when its starburst finally ignites, it's still working with nearly original Big Bang chemistry. That's why this galaxy is such a problem for business as usual. If LAP1b were metal-rich with moderate UV output, it would be another data point, for the universe familiarizes itself quickly. Early galaxies get dirty fast. Instead, it's screaming the opposite. Here is a place where extreme, primitive star formation is still happening hundreds of millions of years after the first stars should have turned on. That stretches our timeline. It says the universe didn't run a single first stars phase and then move on. It kept doing it, in isolated pockets, much later. And remember, everything you know about LAP1b is already filtered through a 100 times gravitational magnification. The intrinsic object is tiny. Without lensing, it would vanish under JWST's sensitivity. The fact that such a small system can be this powerful in ionizing radiation, while still looking nearly metal-free, is exactly the kind of extreme, constrained situation where population 3-like stars can dominate the light budget. So this is why LAP1b has become the main character in this story. It sits at the right redshift, it hides behind the right cluster, it lights up the gas with the right kind of extreme radiation, it suppresses the metal lines you'd normally expect. Its inferred size and star formation history point to a compact, intense starburst. That is not a random alignment of properties. It's a cluster of independent signals, all pointing in the same direction. This could be one of the clearest views we've ever had of a galaxy where population 3-like stars are actually doing the work. But in science, this looks right is not enough. You want a checklist. You want conditions laid out in advance and then tested against the data. You want to know, does LAP1b really meet the theoretical criteria for a first-generation system? Or are we just excited because it feels right? That's where the next step comes in, the 3 conditions test. How you actually decide whether a galaxy is allowed to sit on the edge of being called first generation. How do you stop yourself from just getting hyped and calling every weird galaxy first generation? You don't guess. You don't go on vibes. You put down hard conditions and you see who survives the test. LAP1b does not get a free pass because it feels primitive. It gets interrogated against a checklist that theorists wrote years before JWST ever flew. Condition 1. Extreme UV. If population 3 stars are real, they're not gentle. They are massive, hot, and brutal. They should pump out huge numbers of very high-energy photons. Those photons slam into the gas around them, ionize hydrogen and helium, and make that gas glow in strong emission lines. You don't just look for some UV, you look for a radiation field that is clearly overpowered compared to what normal, metal-rich stellar populations can do. LAP-1-b clears that bar. Its ionizing power is not subtle. When astronomers measure the strength of hydrogen lines and other diagnostics that depend on how many ionizing photons are hitting the gas, they find a level that demands very hot sources. You try to fit it with ordinary stars, you run into a wall. You either need them to be unrealistically extreme for their metallicity, or you admit you might be seeing something closer to the population 3 regime. Very massive, metal-poor stars with fierce UV output. On condition 1, LAP-1b looks exactly like the kind of system population 3 theory has been pointing to. Condition 2, near-zero metals. This is non-negotiable. You can't call something first generation if the gas is obviously full of heavy elements. Those elements don't come from the Big Bang. They come from earlier stars. So the spectrum has to show a serious lack of key metal lines. In practice, that means no strong O3, no strong C3, no normal suite of metal emission you'd expect from standard star-forming galaxies at similar ages. Again, LAP-1b does what it shouldn't. JWST's spectrograph is sensitive enough to pick up those lines if they were there at even modest levels. Instead, what you get is silence. The metal lines are extremely weak or below the detection threshold. Meanwhile, the gas is clearly lit up. Hydrogen is glowing. The ionizing radiation is there. The absence of metals is not because nothing's happening. It's because the gas itself appears to be very close to pristine. That is exactly what you'd expect if the stars doing the heavy lifting formed out of gas that has barely been touched by previous supernovae. Not perfectly zero metals, nature is messy, but far lower than normal early galaxies. Condition 2, passed. Condition 3, the right environment. This is where you check whether the whole story hangs together. It's not enough to have extreme UV and low metals. The surrounding system has to plausibly come from pristine or barely enriched gas. That means the galaxy can't be some giant, evolved object with a long, complicated past. It needs to be small, young, and in a regime where it makes sense that pockets of untouched gas still exist. So astronomers model LAP-1b's intrinsic properties after correcting for the approximately 100 times lensing magnification. They estimate its true mass, size, and star formation history. The result is a compact galaxy with a relatively modest stellar mass, undergoing a concentrated, recent burst of star formation. You're not looking at a massive, long-lived system that's had endless cycles of stars forming and exploding. You're looking at a small, intense object that could easily be drawing from a reservoir of gas that hasn't been heavily recycled yet. That matters. If LAP-1b were huge and old, low metals would be weird and hard to explain. In a small young system, low metals are exactly what you expect if you've only had one or maybe a few rounds of star formation. Perfect territory for population 3 clusters to still show up. Condition 3. This environment is consistent with gas that's pristine or barely enriched. Now step back and look at what just happened. Long before JWST, simulations of early structure formation laid out a prediction. If population 3 stars are there, and you're looking in the right place, then the host systems you find should meet 3 key conditions simultaneously. Insane ionizing UV output, near zero metallicity in the gas, a compact, primitive environment that could plausibly be forming stars from pristine fuel. This wasn't written after the fact to fit LAP-1b. This was in the models. These were the rules of the game. And now you have a galaxy at ZE approximately 6.6 magnified by a foreground cluster that walks straight through that theoretical checklist with all three boxes lighting up. That's why people are tense about LAP1b. It's not just weird, it matches the script. This is what why it matters really looks like. For decades, population 3 stars were mostly aligned in simulations and talks. We think the first stars were massive, metal-free, short-lived, and they did XYZ to the early universe. Now you have an actual object whose observed properties land exactly where those models said a population 3 influenced system should land. It doesn't prove every detail of the simulations, but it slams the door on the idea that these were purely theoretical ghost stories with no observational anchor. But here comes the part you can't dodge, even with all that alignment. There is still no 100% confirmed population 3 stamp you can put on LAP1b. You are not resolving individual stars, you are interpreting integrated light from a whole galaxy. There are always alternative scenarios to test. Exotic stellar populations with very low but non-zero metallicity, contributions from weird binaries, maybe subtle AGN activity, or other extreme but not strictly metal-free setups. Science doesn't let you scream confirmed just because the story is clean. So the language stays sharp but careful. LAP1b is consistent with hosting population 3-like stars. It meets the three main conditions theorists laid down. It's the strongest candidate so far. It is as close as any known galaxy has come to looking like a true first-generation environment. But until you can either resolve individual stars or pin down even more detailed spectral signatures, you live in that uncomfortable zone between incredibly strong candidate and absolute proof. Still, be honest, this is the first time the universe has given us something this on the nose. For a long time, evidence for population 3 was indirect. Chemical patterns in old Milky Way stars, broad constraints from reionization, hints buried in noisy data. Then, JWST arrived and started pushing harder. One target, in particular, showed an early hint, a famously distant galaxy where a strange helium signal appeared, pointing to extreme ionization even before LAP1b entered the scene. You could think of that earlier galaxy as the rumor, the first whisper that something big was out there. LAP1b is the first real suspect. So, what was that earlier clue, and why didn't it close the case? To answer that, you have to go back to GN-Z11, the galaxy that showed the smoke before we saw the fire. What if the first real hint of population 3 didn't come from a clean, simple case at all, but from a chaotic galaxy where a baby black hole and extreme stars were fighting for control? That's GN-Z11. It was the smoke before the fire. LAP1-b is sharp. GN-Z11 was messy. But it was the first time the universe seriously whispered, "They're out there." Start with the basics. GN-Z11 is famous for a reason. Its redshift is about 10.6. Translate that. You're seeing it only around 400 million years after the Big Bang. Not 800 million like LAP1b, half that. This is the universe still in its early scramble, just after the dark ages are breaking. At that time, most galaxies should be tiny, young, and barely organized. GN-Z11 is one of the brightest and most extreme objects known in that era. It's been a problem child from the moment we found it. Then, JWST pointed NIRSpec at it, and things got stranger. When astronomers took its spectrum, they didn't just see standard emission lines. They saw a clump of ionized helium, He2, near the edge of the galaxy. That He2 signal is not some gentle bonus detail. To doubly ionize helium and get He2 emission, you need very high energy photons. That usually means extremely hot, massive stars, or some kind of extreme radiation source. It is exactly the kind of ionization you expect from stars in the population 3 regime. Massive, metal-poor, blasting out brutal, UV. So, naturally, alarms went off. A localized clump of the two. Emission in a galaxy this early, this bright, this weird, is a big deal. It means somewhere in or near GNZ11, there is a patch of gas getting hit with a radiation field far harsher than normal young stars. That immediately put POP3-like cluster on the table as a serious option. People started asking, is this it? Are we seeing a pocket of population 3 stars lighting up a corner of GNZ11? But GN-Z11 is not just about extreme stars. Same galaxy, same dataset, and you also see signs of something even more aggressive. A rapidly growing supermassive black hole. GNZ11 appears to host an active nucleus, a black hole in the middle that is feeding hard, devouring matter at a crazy rate. This is an early, nasty AGN, an active galactic nucleus in a universe that's only a few 100 million years old. That matters because it tells you two things, both heavy. 1. Star formation and black hole growth were already tangled together absurdly early. You don't get to imagine a clean sequence where first you form stars, then later, once things calm down, black holes quietly grow. No. By 400 million years, you already have a galaxy where extreme star formation and a hungry central black hole coexist. 2. It gives you another possible source of extreme radiation. A growing black hole can also pump out high-energy photons that ionize helium. So, the He2 clump might be screaming POP3, or it might be a black hole adjacent effect, or some mix of both. That's exactly why GN-Z11, by itself, couldn't close the case. The helium clump was powerful, but it was indirect evidence. You could interpret it as coming from population 3 stars in a small region. You could also interpret it as gas lit up by radiation spilling out from the active nucleus, or by some combination of hot, low metallicity stars plus black hole activity. The overall spectrum of GNZ11 didn't lock you into one answer. It was exciting, but it wasn't unique. So GNZ11 did two things. First, it proved that the early universe was already insane by 400 million years. Extreme star formation, wild radiation, rapidly growing black holes, all at once. Second, it told theorists the conditions you need for population 3, harsh radiation, low metals, compact clumps, are not fantasy. Environments that could host them really exist at high redshift. But it didn't give you a clean, galaxy-wide POP3 signature. It gave you a loud, ambiguous hint, a smoke signal, not the fire itself. That's where LAP-1b changes the game. With GNZ11, the helium feature is a localized clump in a violently complicated galaxy dominated by an active nucleus. With LAP-1b, you're dealing with a much smaller, simpler system whose entire spectrum leans in the POP3 direction. GNZ11 screams, something extreme is happening here, but it doesn't clearly separate extreme stars from extreme black hole. LAP-1b, on the other hand, looks like a compact starburst galaxy with insane UV, almost no metals, and a primitive environment without a big, obvious AGN signature dominating the whole thing. That's the key contrast. GNZ11 gave you a piece of the pattern. High redshift, crazy helium ionization, early black hole growth, possible POP3 pocket. LAP1b gives you the full combo. Extreme ionizing UV, near zero visible metal lines, and a small, young galaxy that makes sense as a host for nearly pristine gas. GNZ11 said, "The universe can absolutely do this." LAP1b says, "Here is a galaxy that looks like the simulations predicted for POP3 dominated systems." So, you can frame it this way. GN-Z11 is the rumor. It's the whisper that population 3 might be in play. It put everyone on alert. It told us the early universe is not shy about going to extremes, and that helium can light up in a way that hints at very hot, very primitive stars. But it left too many doors open. It couldn't isolate a clean POP3 signal because the environment is too chaotic, too dominated by a monster black hole. LAP1-b is the first solid suspect. It's smaller, cleaner, and more POP3-like as a whole. Its spectrum isn't just a single weird clump. The overall behavior lines up with the three-condition test you actually care about. GN-Z11 showed us smoke. LAP1-b looks a lot more like the fire source. But there's a deeper lesson here. GNZ11 shows how far we can push galaxies. LAP1b shows that we can start matching those galaxies to first star simulations. There's one more escalation waiting in this story. If galaxies can show us integrated signals of population 3, can we go one step further and actually isolate individual stars from that early era? Because once you've used telescopes, lensing, and spectra to hunt populations, the next move is obvious and brutal. Can you catch one single star from the first billion years of the universe and put it under the microscope? To do that, you push lensing to the limit and go after objects like Earendel, the star that might be a lone, magnified survivor in your data, and maybe the closest single-star shot you get at the population 3 regime. What if, instead of just seeing a whole galaxy smeared into a tiny blob, you could actually pick out one single star from the first billion years of the universe and put it under the microscope? Not a cluster, not a blended population, one star. That's the next level of this game, and we're already dangerously close. That's where Earendel comes in. Hubble, not JWST, was the first to catch it. In deep observations of a strongly lensed galaxy, Hubble picked up a point-like source at redshift around 6.2. That means you're seeing this star as it was less than a billion years after the Big Bang. Not a galaxy-scale smear. A single insanely magnified star, or at most a tiny multiple star system, yanked into view by a strong gravitational lens. This is not normal. You are not supposed to resolve individual stars at those distances with Hubble. The only reason you can is because lensing is boosting its brightness by thousands of times. So, what is Earendel, really? That's still the fight. It's clearly massive and hot. The lensing, plus the brightness, plus the colors, all point to a star that is far more luminous than the Sun. Tens of times its mass at least, maybe more. And when you plug those properties into simulations of early star formation, something interesting shows up. There is a non-negligible probability that Earendel is a population 3 star, especially if its true mass sits at the higher end of the allowed range. In other words, if it's really one of those giant early monsters instead of a more modest star, the odds tilt toward pristine origin. That doesn't mean you just slap the label on it. There are plenty of ways to get a hot, bright star without going all the way to population 3. Very low metallicity. Population 2 stars can also be extreme. You can have binary systems, stripped stars, complicated histories. But the key shift is this. With Earendel, you are no longer stuck only with galaxy-wide blended signals. You might be staring straight at one of the individual stars that lived in that brutal early environment. This is where JWST becomes critical again. Hubble could detect Earendel and estimate basic properties, but it can't do the detailed spectral autopsy you need. JWST follow-up is supposed to pin down its mass and spectrum much more precisely. You want to know its temperature, its metallicity, its exact luminosity. If JWST can get a clean enough spectrum, you can ask the hard question: are there metal lines there or not? Is this star just low metallicity, or is it truly operating in a near-pristine regime? If you could confirm Earendel as population 3, that would be a sequence-changing moment. Suddenly, population 3 is not just a population you infer from galaxy-integrated light. It becomes a direct laboratory. One object you can model, test, and argue over in detail. You'd be able to check how a metal-free stellar atmosphere actually behaves, how it emits light, how it compares to all those synthetic models used in simulations. Instead of, these are the properties we think population 3 stars have, you'd be in, this is the spectrum of one, deal with it territory. That's a level of constraint that would smash a lot of uncertainty. Right now, models of population 3 rely on assumptions about mass, rotation, binarity, and mixing processes that we can't calibrate with real examples. A confirmed population 3 star would immediately slice down the range of allowed parameters. It would feed back into everything: predictions for reionization, for early supernova types, for the initial mass function in the first halos, for how fast the universe polluted itself with heavy elements. Earendel also proves something else that's easy to miss. Gravitational lensing plus space telescopes can literally isolate individual stars from the first billion years of cosmic history. That idea used to sound like wishful thinking. Maybe one day, with some ridiculous alignment, we'll see one star that far away. Then it happened. You already have one on the board. Even if Earendel turns out not to be population 3, it shows the method works. It shows nature and our instruments can combine to give you single-star targets at redshift greater than 6. That changes how aggressive you can be. If one such star exists in your data, there are more. If one lensing configuration can amplify a single star into visibility, other configurations can too. It means future surveys, deeper JWST programs, and later telescopes can systematically hunt these objects instead of waiting for miracles. You build strategies around high magnification regions, you monitor them for microlensing events that brighten individual stars, and you pick off single objects one by one. So here's the real takeaway. Earendel might not be the smoking gun for population 3, but it is proof that the gun can be found. It shows that we are technically capable of isolating individual stars from that era and pointing our full physics toolkit at them. The idea of a confirmed population 3 star is no longer fantasy. It's a target. And when you put Earendel next to galaxies like GN-Z11 and LAP-1-b, you see the structure forming. GN-Z11 showed you the early chaos and helium smoke. LAP-1-b gives you a small, primitive galaxy whose whole spectrum looks like a population 3 host. Earendel shows that lensing can pull single stars out of that mess and land them on your detector. But just when that picture starts to look almost straightforward, early galaxies, early stars, lensing boosts, spectral fingerprints, another curveball comes in from theory. Some people argue that the first bright objects might not even be ordinary stars at all. They might be something even stranger. Objects powered not by nuclear fusion, but by dark matter annihilation. If that's true, then some of what we're seeing might not be first stars in the way we think. It might be a different class of object entirely, masquerading as a star. So the next question turns darker. When you stare at these early, overpowered light sources, are you really seeing nuclear fire? Or are you looking at engines driven by dark matter itself? What if some of the first stars aren't really stars at all? What if the light you're seeing isn't coming from nuclear fusion, but from dark matter tearing itself apart? Just when the story seems hard but clean, population 3 stars turning on, reionizing the universe, theorists walk in and drop dark stars on the table. Here's the basic dark star idea. In the early universe, you don't just have gas. You have dark matter halos, big clumps of invisible mass that pull gas in with their gravity. In some models, the very center of those halos can have a high density of dark matter particles. If those particles can annihilate when they meet, they release energy. A lot of it. The idea is brutal. Before nuclear fusion really takes over, a collapsing gas cloud inside a dark matter halo could be heated and powered by dark matter annihilation instead. That delays normal stellar collapse and gives you a very different object. A huge, relatively cool, dark star, powered not by fusion, but by dark matter, self-destructing. So what would a dark star actually look like compared to a population 3 star? Predictions say these things could be more massive, larger, and longer-lived than standard Pop 3 stars. A classic population 3 star might be 100 to 300 times the mass of the Sun, compact and extremely hot, living for just a few million years. A dark star, in some models, can grow even bigger in mass because the extra heating from dark matter stops it from collapsing too quickly. That also means it can stay puffed up and cooler at the surface, radiating more gently in temperature terms, even if the total power is huge. Cooler surface temperature means different spectra and different colors. A population 3 star cluster should look insanely hot and blue in the UV, lots of high-energy photons, strong ionizing output. A dark star of the same total luminosity might look redder, or at least less extreme in the UV, because its surface is cooler and its energy is coming from dark matter. Annihilation spread through a big volume instead of a tiny, blazing fusion core. In other words, same or greater power, but distributed differently, with a different spectral fingerprint. Before JWST launched, people ran the numbers. Could Webb tell the difference between normal population 3 systems and dark stars magnified by lensing? Papers laid it out. Yes, at least in principle. You look at their spectral energy distributions, that's the full shape of brightness versus wavelength, and their colors in different filters. A cluster of hot, metal-free fusion stars gives you one pattern. Extremely blue UV, certain line strengths, certain slopes. A huge, cooler dark star gives you another. Different color, different line ratios, different overall shape. If lensing boosts one of these objects enough, JWST should be able to pick out which class it belongs to. So when a galaxy like LAP1b shows up, this is a real question. Are we seeing normal crazy, very massive metal-free fusion stars? Or dark star crazy, dark matter engines? You can't just assume. You have to let the spectrum decide. Right now, LAP1b looks normal crazy. Its emission is hot and extreme. The ionizing UV power is brutal. The lack of metal lines fits the population 3 narrative. The overall behavior looks closer to a cluster of very massive metal-poor fusion stars than to a cooler, puffed-up dark star prediction. You don't see the softer, redder spectral shape that dark star models usually give. You see something that wants very high temperatures and very strong ionization all over the place. That doesn't kill dark stars as an idea for the whole universe, but it does make LAP1b look like the wrong fit for that category. If LAP1b were powered by huge cool dark stars, you'd expect the detailed spectrum and colors to lean that way. Instead, everything about its light screams, this gas is getting hammered by very hot, very energetic sources. That lines up with classic population 3, unapologetic nuclear fire in metal-free fuel. So, think of it like a murder mystery. You have a body, the glowing gas, and the spectrum. You have 2 prime suspects for the power source. Suspect 1, nuclear fusion in massive metal-free stars. Suspect 2, dark matter annihilating inside dark stars. JWST walks in as the forensic team and starts reading the evidence. The energy of the photons, the color, the presence or absence of certain lines. For LAP1b, the clues point hard at suspect 1. Nuclear, fusion, very massive stars, population 3 conditions. Dark stars don't match the crime scene as well. But here's the twist you can't ignore. The fact that we can even entertain dark matter engines as an alternative shows how extreme these early objects really are. We're at the point where you have to ask whether some of the first bright sources in the universe are running on physics we still only half understand. That's how far out on the edge of the map LAP1b and its cousins live. Once you accept that, there's one more brutal step in this chain. However, these first stars, or dark stars, are powered. They don't last, they end. And when they do, they don't go quietly. They blow the universe open. So the next question is simple and deadly. When these first-generation giants finally die, what do those explosions look like? And how much do they reshape everything that comes after? What kind of star dies so violently that it doesn't even leave a black hole behind? Just raw chaos and heavy elements thrown everywhere. That's the endgame for the most massive population 3 stars. They don't just light the universe, they blow it wide open and rewrite what the gas around them is made of. Take the very top end of the population 3 mass range, not the 30 to 50 solar mass monsters. Go higher. Roughly 140 to 260 times the mass of the Sun. In metal-free conditions, those stars don't follow the usual collapse to black hole script. Their cores get so hot that high-energy photons start turning into electron-positron pairs. That robs the core of pressure support. Gravity suddenly wins harder than usual. The core contracts violently, temperatures spike, and the whole star ignites explosive oxygen burning in one brutal pulse. That's a pair-instability supernova, and it's not a blow off the outer layers and leave a compact remnant kind of event. It completely unbinds the star. No neutron star, no black hole. The entire thing is ripped apart in one catastrophic explosion. All that mass, all that newly forged heavy element material is dumped straight into space. The star doesn't just die, it deletes itself. Now ask how bright that looks from across the universe. Simulations are clear. Pair-instability supernovae are insanely luminous. Way brighter than most ordinary core collapse supernovae. Because the entire star is involved, the energy budget is huge. The light curve, how brightness changes over time, is stretched out and powerful. In principle, an event like this can be visible across cosmic distances, especially if it happens in the early universe and gets magnified by lensing. That's where JWST comes back into the story. The same telescope that can pick out faint primitive galaxies can, with the right observing strategy, catch these explosions. Before launch, teams ran models to estimate how many population 3 supernovae JWST might see. The results were not one lucky event if we're blessed. One study found that with a dedicated strategy, using only a small fraction of JWST's mission time, you could detect on the order of 9 to 15 POP3 supernovae per year. Not hundreds, but not zero. Enough that if you know where to look and you commit to monitoring, you can realistically expect to catch some of these first star deaths in action. So, we're not just talking about a theoretical light show no one will ever witness. We're talking about a type of explosion that is bright enough, long-lasting enough, and distinct enough that JWST could see it at high redshift if the surveys are designed correctly. A population 3 star forms, lives a few million years, then detonates in a pair-instability supernova that outshines its whole host galaxy for a while. In that window, it becomes observable from billions of light years away. But the real impact isn't just the flash, it's what gets left behind in the gas. These explosions are the factories that manufacture the first heavy elements and launch them into their surroundings. And they don't do it in a generic way. The nuclear reactions inside a population 3 star and the physics of a pair-instability explosion produce very specific abundance patterns, particular ratios of elements like oxygen, silicon, iron, and others. Later generation stars that form out of that enriched gas carry those ratios in their atmospheres. That's the chemical fingerprint angle. Even if you never see the original population 3 star or its supernova directly, you can still find its signature billions of years later. You look for ancient, metal-poor stars in our own galaxy and measure their detailed chemical compositions. Some of them show strange element patterns that match what pair-instability supernova models predict. That's indirect evidence that these extreme explosions happened and polluted the gas that later formed those stars. Now, plug LAP-1-B into this. If this galaxy really is hosting population 3 stars at Z, approximately 6.6, that doesn't just mean there are a bunch of hot, primitive stars shining right now. It also means some of them should already be dying. The most massive ones go first. If LAP-1b has stars in the 140 to 260 solar mass range, some of them could already be exploding as pair-instability supernovae, while we're seeing the galaxy's integrated light. That turns LAP-1b into more than a pretty primitive starburst. It becomes a metal enrichment factory, already seeding its environment with the first heavy elements only a few 100 million years after formation. In that picture, the galaxy is not just a fossil of the first star era. It's in the middle of the transition. Some gas is still nearly pristine and feeding new population 3 stars. Other pockets are being contaminated by fresh supernova debris. The system is literally catching the universe in the act of switching from no metals to metals everywhere. Think about the chain. Population 3 stars form from almost pure hydrogen and helium. The most massive of them die as pair-instability supernovae, with no remnant, dumping a specific mix of heavy elements into the surrounding gas. That enriched gas clumps cools more efficiently and forms later generations of stars with different properties. Over time, repeated cycles of star formation and explosion push metallicities up and erase the pristine conditions needed for population 3. galaxies stop being able to make those first-generation monsters. The era ends. If a LAP 1b is really in that phase, it's a live snapshot of that transition. Some of its stars might be the last population 3 objects that region will ever form. Their deaths are what will make future planets and complex chemistry possible there. The stakes are not abstract. You're watching the mechanism that turns a useless hydrogen-helium universe into one that can eventually host rocky worlds and life. And here's the unsettling part. We know most of this not because we've watched hundreds of population 3 stars explode, but because of simulations and models that have been refined for decades. We're working off predicted light curves, predicted yields, predicted rates. LAP 1b and any future POP3 supernova detections are the reality check. Either the universe behaves like those simulations said it would, or it doesn't. So the obvious next step is staring you in the face. Before JWST, the only way to see population 3 stars, their supernovae, and their host galaxies was to grow them inside computers, universe-sized experiments in code. Now that we're getting real data from objects like LAP 1-b, we have to ask, how well do those simulations actually match what the universe is doing? To answer that, you have to go back to the digital side of this story. The supercomputers that have been simulating the first light long before we had a telescope capable of actually checking. How do you trust a picture of the first stars when you can't actually see them yet? Before JWST, the only way anyone saw population 3 stars was by brute force. Build the universe inside a computer and watch what happens. No romance, just code, physics, and insane amounts of CPU time. Here's how that works in plain terms. Cosmologists run full 3D hydrodynamic simulations. That means you track dark matter, gas, gravity, and radiation all at once, in 3 dimensions, over hundreds of millions of years of simulated time. Dark matter collapses first, forming halos. Gas falls into those halos, shocks, cools, and starts to clump. The code follows how dense each region gets, how fast it cools. When it hits the conditions for star formation, how radiation from new stars heats and ionizes the gas, how supernova blow things apart. It's a universe-sized physics experiment running in silico. Inside those simulations, you don't just flag a star formed here. You record the properties of that star-forming region: density, temperature, metallicity. For population 3, you're looking at places where the metallicity is basically zero, just hydrogen and helium. In those zones, the simulations show a very different behavior from what we see in today's universe. The gas can't cool efficiently through metal lines, so it doesn't fragment into many small cores. Instead, it tends to collapse into fewer, larger clumps. That sets up the next key prediction: the initial mass function. The initial mass function, or IMF, is the distribution of star masses that form in a given event. In the Milky Way today, the IMF is bottom-heavy. Lots of low-mass stars, fewer high-mass stars. In population 3 simulations, you get the opposite: a top-heavy IMF. Many more very massive stars than we see around us now. Instead of a swarm of sun-like stars and smaller, you get a population dominated by tens, hundreds of solar masses. That's not a cosmetic detail. It changes everything: lifetimes, radiation output, supernova types, metal yields. So you take this top-heavy IMF, plug it into models for how these stars evolve, and ask, if a galaxy's light is dominated by population 3 stars, what should we actually see with a telescope like JWST? That's where synthetic spectra come in. Theorists build model atmospheres for population 3 stars, metal-free, high surface temperatures, extreme UV output. Then they combine those individual star models according to a top-heavy IMF to get a synthetic spectrum for a whole population. They run those spectra through JWST's instrument response, especially NIRCam's filters, to predict the colors and brightness you'd measure in each band. They also generate color magnitude diagrams, how bright versus how blue-red. Such a system should look in specific JWST filter combinations. By the time JWST launched, the field already had a library of these synthetic spectra. People had already drawn maps. If you see an object this blue in these filters, with this much UV power and this kind of line pattern, that's what a population 3 dominated galaxy should look like. This is not guesswork made up after the data. It's years of pre-computed expectations waiting to be tested. Now jump back to LAP 1-B. You have actual data. NIRC, AM imaging in several filters, NIR, SPEC spectra, lensing corrected luminosity, inferred size. Astronomers take those measured colors and that spectrum and lay them on top of the synthetic models from the simulations. They don't just say, it looks extreme. They literally plot LAP1b in the same parameter spaces they've been using for theoretical population 3 systems. What happens is the important part. LAP1b lands in the population 3 territory those models predicted. Its colors are too blue, its ionizing output too strong, its metal lines too weak to fit normal, metal-enriched stellar populations. When you try to fit it with standard IMFS and typical metallicities, the models struggle or require awkward assumptions. When you let the population be dominated by very massive metal-poor stars, that top-heavy population 3 IMF, the fit gets much better. The spectrum and colors fall into the region labeled, "This is where first-generation systems should be." That alignment is not a tiny detail. It's the difference between "we found something weird" and "we found exactly the kind of thing we said we'd find if the simulations were right." If a LAP1b had landed way off the predicted tracks, too red, wrong line ratios, wrong luminosity for its mass, people would be ripping up their population 3 models right now. Instead, the object slots in disturbingly well. And this is where the payoff really hits. A LAP1b is not just one random weird galaxy that JWST stumbled over in the dark. It's a data point that lands right on top of decades of work. Hydrodynamic simulations that predicted when pristine gas clouds would form. IMF calculations that said those clouds should spawn very massive stars. Synthetic spectra that predicted how those stars would look in JWST's filters. And population models that said, if you ever see a galaxy like this, with extreme UV, almost no metals, and this set of colors, that's your population 3 candidate. Now we're here. LAP1b exists. Its properties are not fighting the models, they're backing them up. That doesn't mean every detail in the simulations is perfect. It does mean the overall framework. First, stars forming in small halos, top-heavy mass function, brutal UV output, rapid metal enrichment. Just got a serious observational anchor. So the story is shifting. Before JWST, you had only theory, universe-sized computer experiments filling the gap where data couldn't reach. Now, you have real light from a real object, at the right redshift, behaving the way those experiments said a first-star host should behave. The simulations are no longer just placeholders. They're starting to look like actual descriptions of what the universe did. And once you have that, the next step is unavoidable and heavy. If LAP-1b really is sitting in the sweet spot predicted for first star systems, what does that do to our timeline of cosmic history? How does it change when we think stars first formed, how long pristine pockets survived, and how fast the universe turned itself from almost empty into galaxies everywhere? To answer that, you have to zoom out from this one galaxy and redraw the big picture. What changes if LAP-1b is the real deal? What actually breaks if LAP-1b turns out to be the real thing? A galaxy where population 3 stars are genuinely doing the work. This isn't a small tweak. This hits the basic story you've been telling about when the universe turned on, how fast it matured, and what kind of objects built everything you see now. Start with timing. For years, the rough story was, first stars light up around 100 to 300 million years after the Big Bang. They run their course, they pollute the gas, and by a few 100 million years in, truly pristine star formation is rare, or basically over in most places. LAP-1b sits at around 800 million years after the Big Bang. If it really hosts population 3 stars, that means pockets of nearly metal-free gas survived way longer than you thought. Not just a short opening act. Hundreds of millions of years of the universe keeping a few zones clean enough to still make first-generation style stars. That stretches the window where population 3 physics is relevant. Instead of, they existed in a brief early flash and then disappeared, you get, they kept popping up in isolated bubbles much deeper into cosmic history. That forces a rewrite of your mental map. You can't treat population 3 as a tiny early spike. You have to think of them as a long tail, overlapping with more normal stellar populations, influencing galaxies for a big chunk of the universe's first billion years. Now hit reionization. The universe went from neutral hydrogen to ionized hydrogen again over a few 100 million years. Something had to supply the high-energy photons to do that. The usual picture is a huge number of small galaxies with normal population 2 stars slowly carved away the neutral gas. Population 3 was often treated as a sideshow. Interesting, but maybe not the main driver. LAP-1b challenges that. If galaxies like this, with extreme UV output and near pristine gas, exist at Z approximately 6.6, the question becomes, how many of these were out there and how long were they active? Massive, hot population 3 stars are UV factories. If they were common enough in early galaxies, they might have contributed a serious chunk of the reionization budget. That changes how you assign blame. Maybe it wasn't just countless normal stars doing the heavy lifting. Maybe a relatively small number of insane, overpowered, metal-free stars punched far above their weight and sped the whole process up. Then there's galaxy formation. LAP-1b is small, compact, and intense. It's not a giant spiral. It's not a huge elliptical. It's a tiny system punching way above its mass. That fits a picture where today's big galaxies are built by merging many little ones like this. If LAP-1b is a template, then you're looking at the kind of unit that might later merge, collide, and mix to help build the ancestors of the Milky Way. That means population 3 stars didn't just flash and vanish in isolation. They shaped the cores of the systems that later merged into the galaxies we live in. In that view, LAP-1b-like systems are the bricks, not the decoration. Their violent starbursts, their early supernovae, their metal production, all of that sets up the conditions inside the small halos that will later come together. The structure and chemistry of today's galaxies would carry that history embedded deep in their oldest components. Now go to chemical evolution. We already know heavy elements come from stars and supernovae, but we've been guessing about the exact yields and timescales for population 3. How fast do they enrich their environments? How much iron versus carbon versus oxygen do they throw out? How quickly does the universe move from almost no metals to you cannot form a population 3 star anymore? A system like LAP-1-b puts hard constraints on that. It's early, but not super early. It looks very low metallicity, but not absolutely zero. That sets the pace. If you can measure its metallicity precisely, compare it to its star formation rate, and maybe one day catch a supernova in it, you can start calibrating those models instead of just trusting simulations. You see how much metal a small, early galaxy can produce over its lifetime. You see how patchy the enrichment is. Some regions still almost pristine, others already contaminated. That sharpens everything from pair-instability supernova yields to the cutoff redshift where population 3 formation becomes impossible. It also forces you to tighten the transition story, not pop 3, then pop 2, then modern stars in neat stages, but a mixed, overlapping mess where pristine pockets, partially enriched gas, and already metal-rich zones coexist for hundreds of millions of years. LAP-1-b sits in that messy middle, and its properties tell you how fast the universe walked that path. And then there's the part that doesn't show up in equations but hits hard anyway. The psychological shift. For decades, population 3 stars lived in slides, papers, and code. You'd see them as colored lines on plots, synthetic spectra in mock JWST filters, cartoon halos on conference posters. Everyone talked about them as if they were real, but nobody had ever seen a system that clearly matched the script. If LAP-1b holds up, that changes overnight. Suddenly, you're not just drawing first-generation stars on a whiteboard. You're downloading data files. You're fitting real spectra. You're arguing over real line strengths and lens models and metallicity limits. Population 3 stops being a theoretical placeholder and starts being an observational category, however cautious the language stays. That shift has knock-on effects. It makes people more aggressive about designing surveys specifically to hunt these systems. It pushes theorists to tighten their models because now they can be wrong in ways you can actually test. It drags population 3 physics out of the maybe someday territory and drops it straight into this is a live, active area with real objects in the sample. It also raises the bar on everything else we think about the early universe. If our predictions about first stars worked this well once, where else are they missing something important? So if LAP-1-b is the real deal, here's what you're left with. A longer, more complicated first star era. A reionization story where extreme stars matter more. A galaxy formation model where tiny, primitive, overpowered systems are the core building blocks. A chemical evolution path that's now pinned to actual data. And a field that has to finally treat population 3 not as rumor, but as evidence. And that leads to the next obvious, uncomfortable question. Now that we have one serious candidate on the board, what happens next? Do we find a few more and get lucky? Or are we about to open the floodgates and turn first star hunting into a statistical science? Because once you've seen one possible population 3 host, the universe doesn't get to hide behind too faint and too far anymore. The hunt only escalates from here. So what happens now that a galaxy like LAP-1b is on the board? Are we done? Not even close. This isn't the end of the story. This is the moment the universe stops being able to hide behind. Too faint Too far, too early. The hunt for the first stars is just getting started, and the pressure is about to ramp up hard. First move, more JWST time, no excuses. Once you have one high-value target, you don't just pat yourself on the back and move on. You go back and tear it apart in more detail. That means deeper JWST follow-ups on LAP-1b and galaxies like it. Longer exposures, more filters with NIRCAM, higher signal-to-noise spectra with NIRSPEC. You're not happy with we see strong UV. You want precise line ratios, tighter metallicity limits, better constraints on the age of the stellar population. You also start doing time variability checks. That sounds technical, but it's simple. You look again, later, and ask if anything changed. Did a supernova go off? Did some region brighten or fade? That's how you catch population 3 supernovae, or rule them out in certain systems. If LAP-1b is a metal enrichment factory, some of those explosions might still be visible as time-variable events in repeat JWST observations. So, deeper doesn't just mean more detail per snapshot. It means watch the thing evolve. Next move, bring in the survey machines. JWST is powerful, but its field of view is small. It's a scalpel, not a net. You need missions like Euclid and the Nancy Grace Roman Space Telescope to do the wide-angle work. Those telescopes will map huge areas of the sky in visible and infrared light, building enormous catalogues of distant galaxies and gravitational lenses. That's crucial because LAP-1b is not magic. It's a product of alignment, a primitive background galaxy behind a massive cluster giving you strong lensing. Euclid and Roman will find far more of those lensing clusters and high redshift candidates. They'll flag the weird, ultra-compact, ultra-blue sources and the strongest magnification configurations. Then, JWST comes in as the follow-up weapon, zooming in on the most promising POP3 candidates for detailed spectroscopy. Wide survey first, sharp scalpel second. That's how you go from one object to dozens. Once you have more than a handful of LAP-1b type systems, the game changes again. You move from, look what we found, to statistical universe building. With a catalogue of POP3 candidate galaxies and maybe even a few candidate stars, you can start asking hard, global questions. How common were these objects? How many galaxies at a given redshift show signs of nearly pristine gas? How often do you see extreme UV with suppressed metal lines? Does that match what simulations predicted for the fraction of halos still forming population 3 at different times? This is where you start testing the early universe models for real. If simulations say only 1 in 1,000 halos should host POP3 at Z approximately 6 to 7, and you find far more, the models are wrong. If they say population 3 should contribute X% of the ionizing photon budget, and your sample demands more or less, you adjust the physics. You're no longer free to tune things until they feel reasonable. The data locks you in. The universe becomes a dataset you can compare line by line to the code you've been running for decades. And this doesn't stop at stars. These discoveries feed straight into the bigger, darker questions. Early black hole seeds, first galaxies, earliest supernovae, structure growth from almost nothing. If LAP-1b-like systems are common, they might be exactly the places where the first massive black holes form, either from direct collapse or from the remnants of some population 3 stars that don't explode as pair-instability supernovae. That ties your first stars to your first quasars. Those same systems teach you how proto-galaxies grow. Are they dominated by short, violent bursts like LAP1b, or by smoother, longer episodes of star formation? Do they quickly merge into bigger halos or remain isolated for a long time? The answers feed into how you think the Milky Way's earliest building blocks formed and combined. And if you start catching POP3 supernovae, pair-instability events, or other exotic explosions, you directly test how the universe injected its first heavy elements into gas clouds that would eventually form normal stars and planets. All of this comes from one basic shift. First stars are no longer just a theoretical phase you mention at the start of a talk. They're an observational target. You can track them through galaxies, through spectra, through supernova, through chemical fingerprints, in later stars. Every new POP3 candidate you add to the catalogue tightens the constraints on everything else. Reionization timing, early black hole growth, the small-end galaxy population, the structure of dark matter halos, the physics of star formation at zero metallicity. And you're sitting in the middle of this shift with a phone in your hand. That's the part that should feel a little heavy. You, a 21st century human, scrolling on a screen, are watching light that left these systems when there were no planets, no carbon-based life, maybe not even any metals at all in parts of those galaxies. When LAP1b's stars were burning, Earth did not exist. The atoms in your body did not exist. The periodic table was barely populated. This light has been traveling for 13 billion years, and it is only now hitting detectors humanity launched a few years ago. For most of history, the question, what were the first stars like, was basically unanswerable. You could guess, you could simulate, you could draw, but you couldn't see. Now the universe is starting to answer for itself. It is handing you galaxies like LAP1b, hints from GNZ11, single-star candidates like Earendel, and telling you, in data, not in theory, this is how I turned the lights on. You're alive exactly when that transition is happening, from ignorance to measurement, from sketches to spectra. The first stars are no longer just a story we tell about the past. They're a live problem, with real objects on the screen, real numbers in the files, and real consequences for how we understand everything that came after. And that's the real cliffhanger. This is just the first wave of results. JWST is still observing. Euclid and Roman are coming. More lenses will be found. More primitive galaxies will surface. Some candidates will fall apart under better data. Others will look even more extreme. Somewhere in that growing pile, the universe is hiding the first unambiguous, no wiggle room detection of population 3 stars. The hunt has started. It will not slow down. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.